where do we get starch? Starch is actually a form of storage carbohydrate. Yeah. So since it is a type of storage carbohydrate, it will be found in the storage organ of the plant. And in human being, starch also, excess starch also will be stored. If we eat a lot of carbohydrate, a lot of starch, you cannot consume and use all the starch to convert into energy. So the excess starch will be also stored in our body. In what form? In what form? Fat. Before that? Glycogen. Yeah. So excess starch will be stored as glycogen. But in plant, the starch will be stored in the storage organ in the form of what? Maybe tubers or roots like potato. So this is an example of starch from tubers or roots. Potato starch, sweet potato, potato tubers, cassava in the form of roots, cassava or tapioca, okay, arrowroot, okay. And another form of storage is in the form of, like this one is cereal. So we have many examples. A lot of commercial starch actually derived from cereal source. Corn, rice, wheat, barley, sorghum, oats. Okay. And another form, our own sagu starch. Somebody said in Emodo, I'm quite happy to see the interaction and the discussion about how sagu palm looks like. So you made me smile actually. But it's good. Yeah? Someone said sagu palm looks like oil palm tree. Someone said look like coconut tree. So, but I don't blame you because maybe most of you you have not seen the actual sagu palm. Yeah? But if you ask me, it looks more like probably coconut. Yes, one day. Have you seen the actual sagu palm? Okay. But it looks more like. But anyway, it's actually the starch here is actually stored in the trunk. Yeah, in the trunk itself. In Sarawak, one sagu palm actually can go up to what 15 meters, yeah, and we can process to get the starch. We can get from one trunk, we can get around 200 to 250 kilogram wet starch, wet flour. But if you go to Papua New Guinea or certain part in Indonesia, we go to this virgin jungle. Nobody has explored that jungle because most of the sagu grow wild. So one sagu palm actually can produce maybe what 900 kilogram, almost 1 ton of starch. So it's a very rich source of starch, and therefore Malaysian government and now Indonesia actually, they want to exploit this as one of the export crop, yeah, to produce. Now Sarawak is still the biggest exporter of sagu, but soon probably Indonesia will overtake Malaysia. Just like palm oil, yeah. Malaysia now is not the biggest exporter of palm oil now. Indonesia is now, because they have a bigger land, they have a cheaper labor, and Malaysia is very generous, transfer all the technology to Indonesia. So now they have become the biggest exporter. Malaysia now is the second one. Yeah. Anyway, these are the source of commercial starch. Commercial means here the starch is being now produced in large quantity. But actually we can also get starch from, theoretically, from any type of plant, any part of the plant, not only in the storage organ, even in the leaf, also we can find some starch. Yeah. skip about the extraction. By the way, this photo was taken when I was in Japan, Hokkaido. I visited a starch factory during a very cold winter, and my digital camera was running out of battery. I was shaking actually, very cold winter in Hokkaido, but managed to take a few photos of starch processing. You can see the heaps of mountains of potato there. Yeah, in Hokkaido they grow a lot of potato, and basically will be processed, and finally we get the starch to cut the story short. Okay, but please read more on this one. And very briefly, let's learn about how the starch is synthesized. Actually, if we learn how the starch is synthesized in the plant, it's really we can see the beauty of nature. If we believe in God, you see, starch is a type of storage carbohydrate. It is synthesized actually from an abundance of energy. We have the sun. The sun actually is a form of energy, and we have a lot of energy that we must be able to capture and store, because we cannot use the energy from sun easily. So we have to store it in some form, so that later if we want to use, we can convert that back to the energy. So this is what the process of photosynthesis that you learn in the primary school. It's a really a powerful and beautiful process designed by God, by nature, to transform energy, the sunlight, combined with carbon dioxide, combined with water, and in the plant, it is converted into a complex polymer called starch. I'm not going to say more about photosynthesis because you are expert probably by now. But during the biosynthesis, during the making of the starch, we need carbon dioxide, we need water, we need the sun as the energy, and we need also a variety of enzymes. A lot of enzymes actually involved in converting the various components into from glucose, as the simplest monomer, and the glucose will be connected through some chemical bond, alpha 1,4 glucosidic, alpha 1,6 glucosidic, and it will become bigger and bigger and bigger, become a big polymer, and it will be converted into a form of small discrete granule. So starch actually present in the form of discrete granule, okay? As small as 1 micron, as big as 100 micron. Average maybe 30 to 60 micron. But some starch actually even less than 1 micron. Very tiny granule. And the synthesis or the biosynthesis of starch actually occurs when we sleep. Yeah? And also during the daytime. So during the night, some of the starch is converted by the enzyme to sugar and transported to other parts. During the day, when there's a lot of sunlight, carbon dioxide and so on, during the day, the starch is synthesized in the leaf. So from glucose will become bigger polymer. Okay? But a big polymer, which is starch, cannot be transported easily to the warehouse, to the storage organ, because it's a big polymer. So during the night, the starch will be broken down into a smaller sugar and transported down to the storage organ, tuber or roots. This is like a warehouse lah. So that's what happens. During the day, it will be synthesized in the leaf, then during the night, it will be transported and stored in the storage organ. Okay. So during the day, the starch is formed as like intermediate form, transit. Macam kita transit kat airport. So we call it transitory starch. It's not really, a very big polymer yet. Only temporary. Then during the night will be broken down again and transported to the storage organ. So during this process, there are a lot of enzymes involved. Many enzymes. Yeah. So it will be stored, in the oops. Tekan. So chloroplast is where the synthesis of starch occurs and will be stored in the amyloplast. So in this, if we look under microscope, this is actually light microscope only. That's how it looks like. So the starch is actually stored in the form of granule. Okay. And these are the, I don't want to go into details of this, but this is basically the synthesis of starch. The glucose unit is connected through chemical bond, covalent bond alpha 1,4 and alpha 1,6. And some enzyme actually involved to produce a long straight linear chain. This is the amylose, and some enzyme involved to form the branch. Okay, so we get alpha 1,6 here and alpha 1,4. Oh, I don't know, the computer or the projector is trying to be funny because they know they are being captured on the camera maybe. Don't be funny. Tak respond pula dah. Come on. Okay, I think you are very familiar with this structure, the chemical structure of glucose, right? In this form. So this is the straight projection of the glucose molecule. We have 6 carbon, and this carbon number 1. Glucose in the present actually in the ring form. Okay, and this carbon number 1, and this is a functional group CHO, also known as CHO, a functional group known as carbonyl group. Carbonyl group is CO double bond O. CHO is N aldehyde. See, you have forgotten your organic chemistry. I know you got an A, but how come you don't know what is CHO? Kalau ketone group macam mana? Okay. So now you recall, that's why you learn all chemistry, organic chemistry. This where and when you have to apply this. This is the aldehyde group. In the solution, when we dissolve sugar, when we dissolve glucose, okay, let's say glucose in this case, when we dissolve glucose in water, it will become a solution. And the glucose ring actually will open up in aqueous solution in water. It will open up at carbon number 1. And carbon number 1 is also known as anomeric carbon. Never heard? Anomeric carbon. ANOMERIC, anomeric carbon. Tak pernah dengar ke? Ada kan? Mesti ada. In organic chemistry, anomeric carbon. And you should learn this in IMG 203, food analysis, when you learn about the properties of reducing sugar. Right? So, why glucose has a reducing property? Because when we dissolve the sugar in solution, reducing sugar, it will open up at carbon 1, which is the anomeric carbon. And the anomeric carbon is actually an aldehyde group. And therefore, glucose will display or will exhibit a typical properties of an aldehyde. Any reaction of aldehyde will be shown, also will be exhibited by glucose. And among other things is the reducing property. So that's why glucose will have a reducing property towards some like phalanx. I think something wrong. Huh? Sorry? This? Yeah, of course. Tick. Okay, never mind. I don't know why. But anyway, in starch, the basic monomer is glucose or D-glucose. This is the unit that actually we call it the building unit. If you imagine a house, the smallest brick, that is the glucose, okay? And it will form a ring structure. And this ring structure not closed forever. In water, in solution, it will open. It will open up at C1. That is the basis of all the reaction of glucose. Do you know that from glucose, we can get hundreds of different chemicals? You can get gluconic acid. From there, you can get, finally, you can get Ajinomoto, the monosodium glutamate, everything can start from glucose. A lot of chemicals, a lot of fine chemicals actually can start from, tick mana? Do not show this message again. I don't think so, but yeah, maybe lah, I think so. Okay. So, D-glucose is also known as D-glucopyranose. Yeah? If you can recall what's the meaning of pyranose and furanose, go back and check again your chemistry. But most importantly is the active aldehyde group at C1. That is the basis of reducing property of glucose, and all the chemical reaction can occur here. Okay. And this carbon number 1, the H group, when it is connected to C number 6, the H and the OH can change position like this and like this. So you can get alpha and beta configuration. So we have alpha glucose, we can have beta glucose, and they show a different chemical properties. So C1 will react with C4 or C6. So we have C4 and we have C6 here. So it can form alpha-1,4 linkages or alpha-1,4 glucosidic bond or alpha-1,6 reducing bond, and we have one reducing end. You see, we have one glucose, one free glucose, we have one reducing end. We have two free glucose, we have two reducing end. We have 10 free glucose, we have 10 reducing end. But when we connect them one by one through alpha-1,4 glucosidic bond like this, we have only one reducing end here. Okay, we have only one reducing end at the end. Okay, because this end has been connected to that end, and that is important to understand. And this alpha-1,4 alpha bond in glucose that form the starch would allow the polymer, because when you have a long polymer, a long chain, it doesn't stay that way forever. It will tend to twist. It will tend to twist and form a helix structure. And the reason for this is because the starch chain wants to attain a stable thermodynamic configuration. So somehow the helix form actually give the stable conformation to the starch molecule, so that it can arrange itself to form a more systematic, more ordered structure. Okay. Boleh pula. So we start from what? Glucose. We start from glucose, and during the biosynthesis in the leaf, we have the enzymes, everything. Some enzyme will help to build the long linear chain called amylose, and some will form a branch chain called amylopectin. And this amylose and amylopectin, these are two different molecules, but they are actually will be packed together in a granule. So they will be arranged and packed together in one granule. So the linear chain of amylose and the branch chain of amylopectin combine together in one granule. Okay, so that is what happens during the biosynthesis of starch. And what happens when you eat something containing starch? You eat the bread contains starch. Starting from the mouth, in the mouth, the saliva contains amylase. The amylase will start to hydrolyze the alpha-1,4 bond. Already the starch actually being broken down. Then goes into your stomach. We have the acid, we have again more amylase, amyloglucosidase will break down the alpha-1,6 bond. And finally, the starch will be broken down finally to what? Break down back to glucose. And the glucose will be transported through the bloodstream to various parts where it will be metabolized and changed back to energy. So imagine that the energy from the sun stored in the form of starch, in the tuber, in the root, in the cereal, we eat, we convert that into product, bread, biscuits, spaghetti, noodle, whatever. We eat the product containing the starch, and now we want to break it down again so that we can get the glucose and convert the glucose into ATP, into the energy, adenosine triphosphate. We get the energy. That's when you learn about all the Krebs cycle. Not Krebs, C-R-A-P. You learn about the Krebs cycle. You have to memorize the Krebs cycle, right? But do you know the significance of that? Now you know. You have to convert that carbohydrate or starch back to energy. So you see the beauty of nature. We trap the sun energy, and we can store for how long, and when we convert into food and we eat the food, we convert that back again to energy. Just try to appreciate, how nature has been designed in such a way. Yeah. Now, the long chain of amylose, they will be twisted to form a helix, and that's how it looks like. The glucose ring has to be in the chair form. We call it chair, bentuk seperti kerusi, right? You learn in organic chemistry. So in that form, only the long chain can be twisted and form a helix. And one round of helix, how many glucose units are there in one round of helix? Yeah? 6. Did not say 6. So then it is 6. So 6 units of glucose per round. Then it will continue. And what will happen if you have a helix, just like a spring, and the cavity or the space in between the helix, here, the cavity inside the helix. So starch itself is hydrophilic, the OH group, because the OH group is hydrophilic. But the space or the cavity in the helix is actually, because of the O oxygen group there, become more hydrophobic. So any molecule that is hydrophobic, such as emulsifiers or fat molecule or long chain hydrocarbon, can be trapped and form a complex with the amylose. And this has its significance. The ability of amylose to form complex is important to to control some properties of starch, and we can take advantage of that. The ability of amylose to form complex has some implication and significance. It can influence the properties of starch. For example, we can add emulsifiers molecule. You learn about emulsifiers in food ingredients. It can form complex with amylose, and therefore it can reduce the or minimize or even prevent the process of retrogradation. So the bread will remain soft for longer time, increase the shelf life of the bread. Okay. And if you remember in the school, primary school, you have a simple experiment. You drop iodine on the bread or something. It will turn dark blue color. And that blue color is actually a chemical reaction where the iodine form a complex with the amylose and form a blue color complex. So that is one simple test to show the presence of starch by using iodine. And amylose structure is simple because it's linear, but it forms a helix structure. What do you think that amylose is really linear? Linear is like this lah. All of you sitting in this one row, straight. Another linear amylose chain. Another. What if we have someone sitting on your head? Start branching. So it's more complex. So that is amylopectin. Amylopectin is more complex. The structure, because we have, in addition to alpha 1,4, we have also alpha 1,6. So it start to branch out, just like the branches on the tree. And because it start to branch, to form a branch, it has a very high molecular weight. Very high molecular weight. Very, very high. Among the largest molecule exists. Apart from cellulose, starch is also, amylopectin is also very big, complex molecule. And the molecular weight can be up to 10 to the power of 8. Yeah, compared to amylose, maybe around 10 to the 4 or 10 to the power of maybe 6 or 5. It's a very big molecule, and it has chain, the branches, and the branches is called chain rantai C or chain C chain, B chain, and A chain. You don't have to know very detail, but just roughly, because when you read any book on starch, when you read anything on amylopectin, you will come across this term, A chain, B chain, C chain. Yeah, so at least you know a little bit, very briefly. But that's very simple. If we think of the amylopectin has a backbone, then the branch will be attached to that backbone. Then we have the chain that is immediately attached to the C bone, to the C chain, is called B chain. Yeah? And the chain that is attached to the B chain is called A chain. As simple as that. But if we look at this structure, we have the inner structure and the outer structure. The inner part of this amylopectin is the C chain, and the outermost, yang paling luar, is A chain. And A chain is the shortest chain in amylopectin, followed by B chain and C chain. And why is this is important? Because amylopectin actually can form a crystalline phase in the starch granule. Remember, a granule always contains amylose, amylopectin. These are the two big polymers that form starch. The amylose is linear molecule, no problem. But the amylopectin is a big molecule, branch molecule, but it can actually form a crystalline phase in the starch. So starch is actually is always described as semi-crystalline. It's not 100% crystalline. It's semi. About 30%, 40% is actually crystalline phase. And which component can form a crystalline phase in starch? In a native starch. Native starch means original starch in the tuber or in the cereal. Only amylopectin can form a crystalline phase, not amylose. Yeah? And which part that form the crystalline phase in amylopectin? So mainly it will involve the outer chain, the rantai A. The A chain is always very important. Yeah? So again, each chain will form a helix structure like that. And this is the alpha 1,6 chain. And each turn of the helix consists of 6 glucose units. And one helix and another helix will be twisted with each other and form a double helix. So this is what the scientists believe the structure of amylopectin in starch. And it's not it's not actually easy to really elucidate the structure of starch, because there are so many different techniques that we need to use until the scientists now able to deduce the structure of starch, polymer, the structure of amylopectin, the structure of amylose. The scientists have been very interested to study about the structure of amylopectin, especially because amylopectin is a complex molecule. So you can see since 1937, there are Haworth, Staudinger, Mayer, Whelan, Range, Mikuni, and finally, not to say finally, but Hizukuri in 1986 or 8. Yeah, he came up with this structure, which is now widely accepted. Hizukuri is a Japanese scientist. His lab is in University of Kagoshima. So I went there in 2000 to work in his lab. But when I was, I didn't know that he has passed away. So when I went there, he just passed away for around 1 year before. So I missed. I didn't meet him, but I worked in his lab, which happened to be very, very small lab actually. So we thought in Japan they have a very good facilities, but actually our lab here is bigger. But their lab is smaller, but they produce world-class research. And this is a structure of, we call it cluster type, tree-like structure, proposed by Hizukuri. So we have C chain, B chain, and so on. Don't worry so much about that. But all you need to understand is this. When starch is being hydrolyzed by acid or by enzyme, what happens during that process is actually the breakdown of the starch polymer. The breakdown of starch polymer means the alpha-1,6 and alpha-1,4 glucosidic bond is being broken down. So you can imagine each chain here will be sort of hydrolyzed and become a smaller chain, and that smaller chain will be further hydrolyzed, and if we allow the enzyme to react to the completion, finally we get glucose. Finally we get glucose. If we wait long enough. Remember rheology? Everything flows if we wait long enough. But what if we don't wait long enough? We don't allow the enzyme to completely hydrolyze the starch, only partially. If we hydrolyze the starch partially, what do you think we will get? Lihun, what do you think we will get if we hydrolyze the starch partially? Partially can mean 50%, 60%, 70%, 20%, 30%. That's the meaning of partially. Let's say we hydrolyze the starch to around 50%. What do you think we will get? Glucose? Maltose? Can we get sucrose? Can we get sucrose from starch? Yeah, Andy? Can we get sucrose from starch? Huh? Sorry? Correct. Betul. Oligosaccharide, yes. But yes, correct, Lihun. We can get oligosaccharide. But just now I asked, can we get sucrose from starch? Can we get fructose from starch? $1 million question. Can we get fructose from starch? No. that sounds very confident. Okay. Who want to support apa ni? Apa lama? Pek Hun. Pek Hun kata impossible to get fructose from starch. I say, I want to listen to Pek Hun, you want to listen to me. I say possible. Have you, you have to put ingredients kan. You know about high fructose corn syrup, right? Or high fructose, well, they call it high fructose corn syrup, HFCS. Where do we get high fructose corn syrup? Starch. From starch. We hydrolyze the starch and we get glucose. Well, not 100% glucose, but high amount of glucose. Then we use enzyme. We use enzyme, isomerize, lupa nama exactly, but it's a type of isomerized enzyme which will isomerize the glucose to fructose. But the starting material is starch. When we hydrolyze starch partially, we will get a mixture of, yes, oligosaccharide and maybe some glucose, some disaccharide, some trisaccharide, some tetrasaccharide, pentasaccharide, hexasaccharide, octasaccharide, decasaccharide, oligosaccharide. Around 20 glucose unit, maybe we can say oligosaccharide. If we have a chain longer than 20, what do you want to call it? Malto-oligosaccharides. You must be familiar, should be familiar with these terms. Okay, we start from monosaccharide, disaccharide, trisaccharide, tetrasaccharide, penta, hexa, hepta, octa, nona, deca. Now, when I learned chemistry in Form 4, my Indonesian chemistry teacher, who was so fierce, that's the first thing we have to memorize. If you don't memorize, by the second day, you have to stand up on the chair. And that's Form 4. So we start to memorize. But between 10 to 20, we call it oligosaccharide. Above 20, we call it malto-oligosaccharide. Okay? So we have to be familiar with those terms. Okay? So you have a mixture of as small as 1 glucose unit, as big as malto-oligosaccharide. And that's what we have in glucose syrup. Glucose syrup or corn syrup. We call it corn syrup, or more general term is the glucose syrup. Glucose syrup that we use in the chocolate, in the confectionery, in some bakery products, and so on. Or maltodextrin. Yeah? Maltodextrin. We will learn later on the ingredients that we can, products that we can get from starch. But anyway, these are the structure over the years. The scientists have tried to figure out how actually the structure of amylopectin. So now, more or less, we have accepted this as the model. But of course, if you read the literature on starch, there are now maybe newer models that have been proposed, because we have more and more sophisticated instrument now which can really study the structure of starch. Yeah? But for now, for this course at least, we just say this is the current accepted structure of amylopectin. And it can get even more complicated, but don't worry. Basically, we have a helix structure. This is the A chain, this cluster, one cluster, we have A chain, B chain, and C chain. Another cluster, another cluster. And they are arranged in a systematic manner, in an ordered arrangement. So when we have something in ordered arrangement, we have a crystalline structure. Yeah, we have a crystalline structure. So the amylopectin, the branches in amylopectin form an organized structure, which become actually the crystalline phase in amylopectin. And what is the evidence? What is the evidence that amylopectin really have branches? So we cannot really see under the microscope that amylopectin has like you don't see that under the microscope. We have to use various analysis. Then from there we will make a deduction. We deduce. Yeah. So for example, from the HPAEC-PAD, this is a type of HPLC, but this high pressure anion exchange chromatography is about $500,000. The cost of the instrument is about $500,000. We don't have it at USM. That's why I went to Hokkaido to learn about this technique. Yeah, and this is what I got. Beautiful result. And what's the meaning of this? When we use this method, HPSEC, high pressure size exclusion chromatography with RI detector, this one is PAD detector, and using these state-of-the-art detectors, we can see that actually, yeah, we get two peaks here. So this bigger peak is actually represent amylopectin, and this smaller peak represent amylose. And that small branches, the small peaks, actually we have glucose, DP12, DP24, DP20, 30, 40. These actually represent or equivalent to the length of the chain, the B chain and the A chain. Okay, but it's a bit complicated. Don't worry so much. The point that you want to understand here is this. All this method actually is a proof. It's a proof that amylopectin is a branch molecule. Okay, that's all. It's a branch molecule. That's what we want to prove here. Okay. So the comparison between amylose and amylopectin, I think I will leave it to you all to go through. But basically, we can say amylose is essentially linear. Amylopectin is a branch molecule. The molecular weight is very different. Yeah, the molecular weight and the degree of polymerization. Do you know the meaning of degree of polymerization? So if I have 10 glucose in one chain, so the dP is 10. Okay, so that is the meaning of degree of polymerization. And we have to understand the differences between amylose and amylopectin, because later when we learn about the functionality or the functional properties of starch, the difference in the amylose and amylopectin actually is very important. And this is why potato starch has different properties with cassava starch. Cassava starch has different properties with corn starch. Corn starch have totally different properties with rice starch. Why? There are many factors. The granule size, the molecular weight of amylose and amylopectin, the structure of amylopectin is different. The chain length of the branch in amylopectin is different from rice compared to rice and corn, and so all these differences would affect the overall properties of starch in terms of the gelatinization property, in terms of retrogradation property, in terms of viscosity, in terms of the stability during high temperature cooking, high shear cooking, low high acid, low pH, high acid condition, and so on. So the basis of understanding about properties of starch, first and foremost, is to understand the properties of amylose and amylopectin and the differences between these two molecules. Just like when we learn rheology, first we have to understand the concept of stress and strain. Here, to understand about starch, we have to understand the differences between amylose and amylopectin. The rest would be easy to understand. Okay, so announcement. Our lecture on Thursday, we have to cancel. But please, happy or not happy, I don't know. But please, always when the lecture is cancelled, there will be some activity in Edmodo. So I want to see more of you participating in the activities, sharing, discussion, helping each other, yeah, on Edmodo. Okay. So I guess I'll see you all next week. Thank you very much.